And so welcome everyone to the 2022 version of the International Workshop on Geometry and Mathematical Physics. So usually we would have this workshop in person, but due to the global situation and the current situation here in Korea, we decided to do this workshop this year fully online. So hopefully next year we can have it in person. And there was a slight change in the schedule. So Professor Shlomo Razamat's talk will be on Wednesday afternoon, and Dr. Dongwook Ghim will be the first speaker of today's morning session. And Dr. Dongwook Ghim is a postdoc at KIAS here in Seoul, and he will talk to us about Toric Calabi-Yau fourfolds and 2D 0,2 theories and Brane Bricks. So please go ahead.
Thanks for the invitation. I'd like to thank the organizer for giving me an opportunity at this nice workshop to present my recent research with Rak and other people. So today I'm going to talk about Toric Calabi-Yau fourfolds, 2D 0,2 gauge theories, and Brane Brick. So this talk is basically based on work with following archive numbers and collaboration with Sebastian Franco, Azim Hassan, Sang-Min Lee, Rak-Kyeong Seong, and Daisuke Yokoyama, and many others I did mention here. So yeah, basically this talk is about Brane Brick models. So I think that most of you are not familiar with what this is. So today I'm gonna try my best to make this talk pedagogical so that all the newcomers can understand the basic topics in what Brane Brick model is. Furthermore, I think most of you, conversely, most of you are familiar with the so-called Brane Tiling. So I think I try to make this talk as so that this talk can show the interaction between tiling business and Brane Brick business. In other words, 4D n=1 supersymmetric theory and 2D 0,2 supersymmetric gauge theory. And if time permits, I'm going to introduce the enumerative tools in 2D gauge theory, which is called Elliptic Genus, and its modified version in the context of Brane Brick models. Yeah, this is the basic setup of Brane Brick. So Brane Brick model is a low energy effective theory of D1 branes, which probe a Toric Calabi-Yau fourfold cone, and it shows 0,2 supersymmetry. So this is basic setup. We fill up 0 and 1 direction of 10-dimensional space-time with D1 branes, and fill up rest 8 dimension with the Toric Calabi-Yau fourfolds, which have singularity at origin. And the nice geometric property of Toric Calabi-Yau fourfold is, by definition, it has 4 isometries along these angular directions. And this will correspond to U1R times U1 cube global symmetry of gauge theory, which emerges on this D1 brane as a world volume theory. And if we have n D1 branes, stack of n D1 branes coincident at this origin, we have rank n gauge theory in general, or more higher theory, depending on the type of Toric Calabi-Yau fourfold we put. So you might say, why Brane Brick model is important? This is one partial answer I can give you. So whereas many 0,2 supersymmetric models are fragile, which means that in low energy, the UV supersymmetry is broken, spontaneously broken. So, but models from D1 brane or D1 probe seems robust in the infrared. It shows geometric phase mostly, and also toric property of the Toric Calabi-Yau fourfolds implemented to gauge theory provides various manipulation leverage in gauge theory itself. And this is basic schematic diagram showing the location of Brane Brick models in the big landscape of 2D gauge theory. So we can engineer many different 2D supersymmetric VFTs in the framework of string theory. And because string theory suggests 10-dimensional space-time, and if we divide the 10 to 2 plus 8, then the rest 8-dimensional situation can govern the rest 2-dimensional supersymmetric theory. So if we put on Calabi-Yau fourfold on 8-dimensional, transpose 8-dimensional, then we have 0.2 supersymmetric gauge theory on 2 dimensions. And Brane Brick model corresponds to special class of 2-dimensional 0.2 gauge theory, which emerges with Toric Calabi-Yau fourfold at its transverse direction of D1 brick. As I mentioned, this class of theory shows U1 cubed non-arc global symmetry, and yeah, this is one comment. And another comment is that this Toric Calabi-Yau fourfold is usually described by a combinatorial tool, which is called toric diagram. So this is the example of the toric diagram. So the most easiest, the easiest one of easiest example of Toric Calabi-Yau fourfold is C4, and the toric diagram looks like this. This is nothing but minimal tetrahedra of C-cube lattice, and other Calabi-Yau fourfolds has toric diagram. Toric Calabi-Yau fourfold has toric diagram, and it is well known that conical geometry of Toric Calabi-Yau fourfolds is described by this lattice diagram, which is defined on C-cube lattice. Actually, for 4-dimensional manifold, toric 4-dimensional manifold, this diagram is defined on C4, but using Calabi-Yau condition, we can project one common direction so that the diagram is depicted on this C-cube lattice. And because of geometric property, this diagram shows SL4Z redundancy. So even if we tilt this diagram with SL4Z matrix, then its shape changes, but the corresponding geometry remains same. You can see various shape of toric diagram. And yeah, in principle, this can be whether convex or concave, but in this talk, we are gonna think about only convex type of toric diagram. And this is basic review of 2D 0.2 supersymmetric gauge theory I'm mentioning today. So this is basic structure of supersymmetric multiplet of 2D 0.2 theories. There are following 3 types of multiplets. One is chiral multiplet, where on-shell degrees of freedom is this phi, complex boson, and psi plus white moving fermion. On the other hand, in addition to this chiral multiplet, in 0.2 theory, there is also another meta multiplet called Fermi multiplet, whose on-shell degrees of freedom is just left moving fermion. This does not have bosonic degrees of freedom on-shell. Also, there are vector multiplet because we are engineering gauge theory, and the on-shell degrees of freedom here is gaugino, which is left moving fermion. And we can employ quiver notation to represent by fundamental or gauge theory. Yeah. So here in the quiver notation, yellow node corresponds to vector multiplet, and we assign U1 or UN gauge group to each nodes in this talk. So in general, we can assign other gauge group as well. And this black arrow will describe chiral multiplet, which has by fundamental charge under this UNI or UNJ gauge group. And Fermi multiplet will be noted with this red arrow, given by this. And because the Fermi multiplet is also charged, in principle we can use this directional arrow here, but there is kind of a flip symmetry in the Fermi multiplet, so we can flip lambda and lambda bar with the appropriate manipulation of the interaction terms. So it is a well-known convention that we can omit this arrow in case of Fermi multiplet. And like swap potential in 4-dimensional minimum supersymmetric theory, we can introduce holomorphic interactions between matter fields into these 2 ways. So one is called E-term. So this is allowed deformation in chirality condition of Fermi multiplets. As I mentioned a bit ago, Fermi multiplet is given by this, and its on-shell degrees of freedom is left moving fermion. So it should satisfy the chirality condition, which is described by this way. The bar lambda go to be 0 in principle, but we can deform a little bit with the holomorphic function of chiral multiplets, so-called E. And J term is derivative of swap potential. So this is real analog of 4D N=1 theory swap potential. in the Lagrangian, it can be coupled with Fermi multiplet this way. So the upshot is for each Fermi multiplet, we can introduce two types of holomorphic interactions. One is called E term, and another is called J term. And because we deform the potential, the chiral condition of Fermi multiplet, we need to check whether it is consistent with supersymmetry in the end. So we cannot just randomly assign E and J term, but we need to assign them satisfying this trace, so-called trace condition, which says trace E times J, and sum of this for all the Fermi multiplets should vanish. Yeah, now let me begin talking about D1 branes and its word volume theory. So let's assign C4 as a transverse manifold. Then we can have the simplest version of Brane bricks. So the word volume theory of D1 branes probing C4 is given by just maximally supersymmetric Yang-Mills theory in 2D. And this is also obtained by dimensional reduction of 10-dimensional n equal 1 for Yang-Mills theory. So its meta content is given by this UN gauge group, where when there is n D1 branes are probing Toric Calabi-Yau 4, just C4, and there are 4 adjoint chiral fields and 3 adjoint Fermi multiplet, which are all adjoint under this UN gauge symmetry. And the number of these Fermi and chiral fields are obtained by just decomposing the 10-dimensional n equal 1 vector multiplet into 2D 0,2 meta multiplets. So there are 8 transverse directions. So in case of gauge field in 10D, it has 8 components along the transverse direction. And because the C4 has SU4 symmetry, we can divide this as 8 vector multiplet in vector representation spin 8 group into 4 plus 4 bar representation on the SU4. And similarly, we can repeat similar thing for gaugino partner, supersymmetric partner. Then spinor and conjugate spinor is divided into this way. So these 2 upper cases classes will give chiral boson and right moving fermion with this kind of global symmetry assignment in 2D, and this will be combined into 0,2 chiral multiplet. And also there are this kind of 6 left moving fermion, and 2 of them are paired into 0,2 Fermi multiplet. So we have 3 adjoint Fermi in there. Also, you can see there are 2 fermion, additional left moving fermion, which is not charged on the SU4 global symmetry, and this will make gaugino, which belong to this vector multiplet here. Also, interactions between these meta multiplets and gauge field is dictated by 10-dimensional super Yang-Mills commutator. And as you see, the interaction is given by this way. So this is nothing but commutator-like form. As I mentioned, there are 2 types of interactions we can turn on, J and E, and both of them are inherited from the commutator of 10D. And one thing I like to mention is that for all the classes of theories I'm going to mention today, the interaction shows Toric condition, which is the necessary condition for theory to show U1 cube global symmetry in the end. So Toric condition is nothing but this is the condition on J and E terms, in addition to the trace condition I mentioned for supersymmetry. So this Toric condition says each J and E are given by the difference between 2 monomials. Like this is one monomial and this is another monomial. And in case of E, this first term is the monomial and the second term is another monomial. So all the J and E are described by J plus minus J minus and E plus minus E minus like this. And you can see, you can wonder what's the role of C4 in this 2-dimensional gauge theory. And it is easy to check that the classical Masonic moduli space of this theory is given by the C4, because all the interactions here are classically trivial. So this is, in case of U1 gauge theory, everything becomes C number, and this is nothing but just trivial equations. So there are no constraints on X, Y, Z, D for chiral multiplets, and we can generate, we can identify these 4 chiral fields as a basis of C4. So you can see these chiral fields and classical Masonic moduli space they generate is C4, which is the probed manifold of D1 branes. And this is the quiver diagram, which shows 4 chiral multiplets and 3 Fermi multiplets and gauge nodes here. And but one of the drawback of this quiver diagram is it nicely encodes the representation of the gauge symmetry, but it doesn't show the global symmetry structure. I mentioned the SU4 structure of theory. Also, it cannot express the interaction term in an efficient way. So as an alternative, I'm going to suggest periodic quiver, which makes these two properties very manifest. So this is periodic quiver of C4 theory on a 3 torus. Basically, periodic quiver is quiver diagram defined on a 3 torus, which shows periodicity along X, Y, and Z direction. And you can see 4 chiral multiplets that was present here is represented by black arrows, like given by X, Y, Z, and D on this left-hand diagram. And the periodic quiver is just not drawn just for aesthetics, but the direction of this chiral fields in this 3 torus is dictated by the SU4 symmetry they are charged. So we can look at 3 cartons of SU4 symmetry and assign the displacement along X, Y, and Z direction to each chiral fields, so that the carton, so that its charges, each field's charges on the carton becomes manifest on this diagram. Also, in case of Fermi multiplet, we can repeat something similar to draw this periodic quiver on a 3 torus. One nice property of periodic quiver is that it also encodes not just global symmetry, but the form of interactions, J and E terms in its shape. As I mentioned, because of toric condition, J and E terms are given by difference between 2 monomials like this, and each of them is associated to 1 Fermi multiplet. So given Fermi multiplet, we can associate this kind of plaquette structure with encoding J and E terms of interactions. For instance, J plus can be encoded by these red plaquettes, and each of them will represent a chain of chiral multiplets which belong to J plus and J minus respectively. And in case of E terms, we can do something similar, so that this chain of chiral fields are given by E plus, and another chain of chiral multiplets is given by E minus, so that E plus minus and J plus minus, which are constituent of interactions, looks manifest in this cube. And one nice combinatorial property is that the graph dual of periodic quiver is so-called Brane Brick. So this is the main object. Both periodic quiver and Brane Brick are main object of today's talk. But as you see, this is actually a 3-dimensional diagram. So it's a bit hard to visualize everything. So most of the case, I'm gonna stick to this periodic quiver instead of Brane Brick. But still, Brane Brick has its importance because in string perspective, Brane Brick naturally appears in T-dual picture of initial configuration. So initial configuration was given by this, with D1 brane occupying 0 and 1 direction, and Toric Calabi-Yau 4 folds occupying 2 to 9 direction among 10-dimensional space-time. But if we take T-duality 3 times, then we can introduce T4 branes and NS5 branes, where NS5 branes wrap a holomorphic cycle of Toric Calabi-Yau 4. And T-dualized Toric Calabi-Yau 4. And you can see this Brane Brick model emerges as the location of D4 and NS5 branes along this X2, X4, and X6 angular directions. And here in the Brane Brick, the gauge group will correspond to the bulk of brick inside or outside of the brick, depending on the convention. And chiral fields are so-called oriented surface, and Fermi fields will be unoriented ones. And this situation is very analogous to the 4-dimensional N=1 gauge theory, which emerges in D3 brane, probing Toric Calabi-Yau 3 folds, not 4 folds. There, we have so-called Brane Tiling, which is a combinatorial tool capturing the physics of 4D gauge theory. So Brane Brick is the analogous of a Brane Tiling. But tile is defined on 2 torus, but brick is defined on 3 torus. And there also we could associate this two-dimensional toric diagram, which describes the singularity of Toric Calabi-Yau 3 with this Brane tile, and the quiver diagram of a four-dimensional n=1 gauge theory. And we can repeat something similar in a slightly different dimension. So we have three-dimensional toric diagram, and periodic quiver is also defined in 3 dimensions on a 3 torus, and Brane Brick is also defined on a 3 torus. And this is middle wrap up of my talk. So I suggest how Brane Brick how Brane Brick configuration is cooked up given the data of Toric Calabi-Yau 4. And we can see this is direct dual of periodic quiver, which encodes interaction and global symmetry structure of gauge theory very nicely. And as I mentioned, this is expanded version of quiver diagram, which only encodes the gauge representation on a 3 torus. And you can see, as I mentioned, Brane Brick model also naturally arises in strength perspective as a T-dual picture of this Toric Calabi-Yau. And Toric Calabi-Yau 4 is described by a 3-dimensional toric diagram, which is defined on Z-cube lattice. And as I mentioned, the mesonic moduli space of the gauge theory arising in D1 brane is the Toric Calabi-Yau 4-fold the Brane was probing. So this is the relation between various combinatorial tools and graphs. And today I'm going to talk about how this relation can be expanded to cook up more general 2D 0,2 gauge theories for more general Toric Calabi-Yau folds. Is there any questions so far? No. Yeah, and because most of our audiences will be familiar with Brane Tiling, let me mention some developments in this frontier facilitated by tiling business. So I'm going to mention how to cook up more general 0,2 gauge theories, starting from the tiling or 4-dimensional n=1 gauge theory. So there are 3 main methods I'm going to mention today. One of which is called dimensional reduction, Orbifold reduction, and 3D printing perspective. So I'm going to mention this way and this orders. So first, I'm going to briefly sketch the Orbifold of C4. Actually, this Orbifold class has, in principle, nothing to do with tiling. But this example was listed because this is a nice example which can show the utility of periodic quiver. So gauge theory corresponding to Orbifold of C4 manifold is obtained by identifying period of periodic quiver according to Orbifold action. Let me show this with explicit examples. There are 2 types of Z2 Orbifold of C4. One in action is defined this way, 0011 and 1111. So each action acts on the different components of C4, 4 components of C4. Whereas there are only 1 type of Orbifolds. Sorry. Yeah, let me keep with this. So in case of 0011 theory, the identification rule is given by this. As I mentioned, this was the periodic quiver of C4 theory, and all the nodes, 8 nodes, were identified into single nodes in case of C4. But if you are interested in Orbifold of C4, which action is defined this way, then you can identify gauge nodes here into different ways, like this upper 4 nodes as single gauge nodes, and this lower 4 nodes with another gauge node. And again, because of periodicity, this lower gauge node is defined by node 1, and these 8 nodes are defined by node 2, with the identification of 2 different layers. And here 1, because 1 acts on Z, so along Z direction or Z displacement, we meet, for each displacement along Z direction, we meet different gauge nodes this way. But along X or Y displacement, there is no action over Orbifold, so we don't meet new gauge node. We just remain at the same node. So this is one identification we can make for this Orbifold action. And compactifying this periodic quiver into just plane, then we can cook up this quiver diagram for Orbifold corresponding to C2 Orbifold of C4 with this section. And similarly, for another action defined by 1111, we can identify many different nodes into this way. For instance, along X, Y, and Z direction, and even this diagonal movement, we can face another nodes after this one movement. Then we can, one identification is given by this way, and compactifying this periodic quiver into single diagram, we can cook up this quiver diagram. So this is one utility one can play with Orbifold. As you see, for different action of Orbifold, we can obtain different quiver diagram for gauge describing D1 brane, world volume of D1 brane. But Orbifold is just only a small fraction of possible Toric Calabi-Yau fourfold. As I mentioned, there are so many diverse shapes of toric diagrams, and we can associate different manifolds with different complex four-dimensional manifold for each diagrams. But many of them belong to class of this kind of dimensional reduction, or Calabi-Yau 3 times C type, or the Orbifold of Calabi-Yau 3 times C. So one observation is that many of the toric diagrams for Calabi-Yau fourfold can be drawn from lifting up several points or dragging down a few points of planar toric diagram for Calabi-Yau 3. As I mentioned, toric diagrams for Calabi-Yau threefold is given by this planar thing, but data of toric Calabi-Yau fourfold is given by this bulk thing. And we can cook up several of toric diagrams of toric Calabi-Yau fourfold by lifting several points of data of toric Calabi-Yau 3. For instance, this cone shape can be cooked up by lifting the central points of this hexagon like this, and this cone like this diamond-like thing can be cooked up by lifting several points and dragging down of origin by one. Also, we can cook up more general shape of diagrams like this by lifting several points simultaneously. And this kind of geometric operation can be translated into physics. And this is a way to cook up more general 0,2 theories from four-dimensional equal 1 theory, which was associated to this planar toric diagram. So the first one is called dimensional reduction, whereas the second and third one is called Orbifold reduction and 3D printing. So as I mentioned, 4D and equal 1 theory can be easily described by combinatorial tools, so-called Brane Tiling. And this is the basic example showing how Brane Tiling emerges in this flow of algorithm chart connecting gauge theory and toric diagram. So on the right-hand side, we have planar toric diagram, and on the left-hand side, we have quiver diagram of 4D and equal 1 gauge theory arising in D3 brane forming toric Calabi-Yau threefolds. And periodic quiver and Brane Tiling is kind of bridge connecting these different concepts. And there is so-called forward algorithm, which can compute these diagrams one by one, beginning from this quiver diagram and interaction terms, which is described by holomorphic swap potential in case of 4D and equal 1 gauge theory. Yeah, So before proceeding, let me mention one thing. So here, geometrically, the operation we need to do to cook up this kind of bulk toric diagram is to identifying the vertices of planar toric diagrams first, and lifting few of the vertices in through the direction we want, right? So the first thing we need to do is to identifying, what's the meaning of vertex in the gauge theory side. So this is a nicely encoded Brane Tiling. So the perfect matching is the answer, and perfect matching is a combinatorial tool Brane Tiling provides us with, and it assigns the collection of chiral fields to each vertex of the toric diagram. So let me explain you with this Conifold example. So in case of Conifold, if you look at the swap potential, we can associate x12. We can easily identify this x12 as one perfect matching because it appears each term in the swap potential only once. And similarly, y21 also provides one perfect matching, and y12 and x21. Each different chiral fields construct one perfect matching in case of this theory. And these are identified as external vertices of toric diagrams like this. And so combinatorial rule we need to do when lifting this one vertex into z direction, is doing something to chiral fields corresponding to this perfect matching or vertices. So in case of geometry, on the geometry side, we lift just one vertices by height 1 to cook up toric diagram of conifold times the C manifold. And periodic quiver side, we had planar periodic quiver in case of tiling theory or 4-dimensional theory. And what we need to do is to add z direction of the periodic quiver so that we can cook up this bulk periodic quiver, 3-dimensional periodic quiver on a 3 torus. The actual rule is slightly more complicated. First, we need to find what kind of chiral fields correspond to this vertex by referring to perfect matching in tiling. And in addition to that, we need to add more this z direction arrow, because actually this is because as you can see in the dimensional reduction, 1 for the chiral multiplet is decomposed into 1 chiral multiplet and Fermi multiplet in case of in the language of 0.2 theory, whereas 1 vector multiplet is decomposed into 1 vector node in addition to this adjoint chiral multiplet in the language of 0.2. And this z direction arrow corresponds to this adjoint method. And also we need to give z displacement in case of chiral fields corresponding to this special perfect matching. And as I mentioned, because this chiral multiplets in 4D theory was decomposed into chiral plus Fermi multiplets in case of 0 to language, in terms of 0 to language. So we need to assign more Fermi multiplets for another chiral fields as well. Following these concepts, following this rule, we can simply obtain this periodic quiver on a 3 torus describing conifold times C manifold. And we can consider a more complicated operation. For instance, we can lift one point not just by height 1, but height n in general, or dragging down it into simultaneously with lifting like this. Also, we can slightly generalize this operation. This is what we call Orbifold reduction. An extension of this block periodic quiver along z direction is done by this way. As I mentioned, by the procedure I mentioned earlier, we can cook up one cell. And in case we lift more than, in case we lift this vertex more than height 1, then we can glue more of this. We can glue many building blocks simultaneously and identify gauge nodes differently. Then this is the combination of these 3 diagrams or overlapping of these 3 diagrams will give periodic quiver corresponding this toric diagram. In case of dragging down, we can identify, we can assign different z displacement for the chiral fields associated to this perfect matching. For instance, previous case, lifting case, we assigned this -1 z displacement to these chiral fields. But this case, we can assign +1 or -1, depending on the number of, or depending on the height this one vertex is moved. But this does not exhaust all the list of possible Toric Calabi-Yau fourfolds. So there are several Toric Calabi-Yau fourfolds which cannot be reached through these 3 different combinations of methods. The one nice example is so-called Q111, which Toric diagram is described this way. In case of this theory, we cannot reach at this diagram just by lifting 1 point along z direction. For instance, we can cook up this Toric diagram as dimensional reduction of a conifold without this upper part. But because of this upper half, the presence of this upper half part of Toric diagram, we cannot reach at Q111 only by resorting to this the 3 method I mentioned earlier. So one additional method I'm going to mention in the remaining time is so-called 3D printing. So this is extension of Orbifold reduction to many vertex case. And there are also another method called Higgsing, which is inspired by gauge theory, but I'm going to mention about this today. Sorry, I'm not going to mention about this today. Yeah, 3D printing is basically is defined by this way. It's the operation that accumulates new vertices on top or below of vertices in a planar toric diagrams. So the only operation I mentioned is just touching one vertices of planar toric diagram. But this case, we can consider situation we touch many vertices of planar toric diagrams simultaneously. For instance, by lifting 2 points of conifold toric diagrams simultaneously, this way and this way, we can cook up the toric diagram corresponding to Q111. And this operation will be also translated into gauge theory side by a different identification or different displacement rule assigned to each chiral fields. For instance, these blue points are lifted by 1, and this will give this kind of building blocks with upper Z displacement assigned to chiral fields corresponding to this perfect matching. And for this green vertices, this point is dragged down to cook up this Q111. So we can assign -1 Z displacement to chiral fields associated to this vertices. And we can accumulate these 2 different building blocks, identifying these 2 layers to cook up periodic quiver of Q111. The actual process is slightly more, slightly more complicated because we need to identify several arrows as well on the layers and erase some of them when it gets messed. But this is technical detail. The basic structure was given by this, as I mentioned. So one might ask that except for dimensional reduction, the 2 methods I mentioned is not that healthy in a sense that they might generate gauge anomaly in general. Yeah, but in many explicit examples, fortunately, there was no gauge anomaly. And if you look at the detailed algorithm, it's enough to check that whether plus-minus layer generates gauge anomaly in case of orbifold reduction. Yeah, by plus-minus layer, I mean the layer in between this plus Z displacement was assigned and minus this Z displacement was assigned to chiral fields corresponding to special perfect matching. And in case of 3D printing, similar check is necessary model by model at the intermediate layers of distinct building blocks. So in general, our method does not guarantee that the resulting theory is anomaly-free, but many examples, anomaly doesn't show up in explicit examples. And also, most of the gauge group is not anomalous in the construction, but we just need to sum of them to check whether the full theory is consistent without anomaly or not. Yeah, time is almost done, but let me briefly explain about what elliptic genus is. So elliptic genus is one enumerative tools we can turn on in case of 2-dimensional gauge theory. So its definition is given by this way. This is nothing but trace over Ramon sector with periodic boundary condition assigned to each fermions. And this is kind of twisted partition function with -1 to the f assigned due to this periodic boundary condition to fermions. And we can refine more with additional fugacities associated to global symmetry. In case of our theory, we had U1 cube non-R global symmetry, so we can turn on fugacities corresponding to it. And thanks to supersymmetry, our theory enjoy this partition function is Q bar independence, even though we turn on Q bar here, which measure the right-handed, right-moving Hamiltonian. And it's invariant under small deformation, so it's basically coupling independent. And because we are thinking of 2-dimensional theory or torus, this theory has modular property. And one nice observation we made in case of Brane Brick model is that there are 2 possible computations to capture elliptic genus. And one is canonical one defined by, derived by localization method. And this is nothing but, this is description made by JK residue with some complicated integrand inside. And but the new method we can suggest in case of 2D 0.2 theories in Brane Brick model class is that so-called geometric methods. So we can triangulate this toric diagram first and assign special factors to each minimal tetrahedron, which is the building blocks of this toric diagram. Then just by summing over this assigned pieces, we can recover the residue answer of elliptic genus. So the first method is quite time-consuming because of this JK residue prescription. The second method is very straightforward. So this is just O1 time computation. Yeah, so this is what I prepared. Yeah. Thanks for listening.
Thank you very much, Dongwook. Are there any questions?